Hello. In this session, we'll go with D block elements. I'm your Laxma Reddy sir. We'll have some plus two JEE mains, JEE advanced, and NEET examination purpose D block elements. The discussion of D block elements. D block, S block elements, and P block elements. All these are memory based. Maybe there are some important facts, some important reactions, some important oxidizing type of reactions of KMNO4 or K2CR2, but majority things, if you see, they are memory based. So how to remember such things and what are actually to be memorized? Okay, now you can see a lot of data I have written because I can't remember all those, and there is no need. When I have written, that means I am not remembering any of this, so there is no need for the student also to remember any of this. Fine, that is first thing. So here we'll go with the D block elements. What are actually D block elements? What are the important lines of D block elements, and what a student is to remember? Because S block, P block, D block, and F block elements are there, and from D block elements, one or two questions you can expect in all entrance examinations. But the interesting thing is when the question is coming from the D block elements, that is actually related to most of the times to complex compounds, because all complex compounds are mostly formed because of the D block elements. So that question you can say even of the D block elements also. Fine. So let's go with the D block elements. First of all, D block elements means the elements in which the differentiating electron entering into the D orbital. We have S orbitals, P orbitals, D orbitals, and F orbitals. If the differentiating electron, that means the last electron, the newly coming electron, if it is entering into the D orbital, they are called D block elements. Okay, D block elements. So we have 3D series, 4D series, 5D series, and 6D series. The meaning of 3D series is the differentiating electron is entering into the 3D orbital. 4D series means the differentiating electron is entering into the 4D orbital. Similarly, if it is entering into the 5D orbital, 5D series, 6D orbital, 6D series. You can see here scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. In all these, you can see the electronic configuration I have written here 4s2 3d1. Later, I have mentioned 2 2 2 3 1 5 like that. Okay, now that means the electrons are entering into the 3D orbital. So all these elements, okay, these elements are, this is the first row elements are called 3D series elements. The next row is this one, yttrium, zirconium, niobium. In this case, if you see, the differentiating electron is entering into the 4D orbital. So this series is called 4D series. 4D series. Similarly, lanthanum series is called 5D series. Actinium series is called 6D series. Remember, lanthanum and actinium are D block elements, not F block elements. Lanthanum is a D block element. Actinium is also D block element only. We generally discuss lanthanum and actinium along with the lanthanides and actinides because some similarities are there. Okay, but actually lanthanum and actinium, they belong to D block, not F block. So this is 3D series, 4D series, 5D series, and 6D series. These are the elements. No need to by heart this last row, but these three rows you need to remember: zinc, cadmium, mercury, copper, silver, gold. Okay, na Au, Rm, nickel, palladium, platinum, cobalt, rhodium, iridium, iron, ruthenium, osmium, manganese, technetium, rhenium, chromium, molybdenum, tungsten, vanadium, niobium, tantalum, titanium, zirconium, hafnium, scandium, yttrium, lanthanum, and actinium. These elements are Rutherfordium, dubnium, seaborgium, borium, hussium, meitnerium, damstadium, rhodium, and copper. This is also completely filled. Previously, it was given like it is incomplete one, but it is also completely filled. Total, you can see there are 40 elements. 10 into 4, 40 elements are there. About their atomic numbers, about their electronic configurations, about their atomic radius, about their ionization potentials, about their atomization enthalpy. All these we'll discuss in this session. Very, very interesting. And look at all these numbers. No number is important. Just for reference purpose, just to give you the idea what is given in the NCERT, I'm just showing all this, but no need. You can remember all these points as I am going to say. First one, very interesting one is electronic configuration. Scandium electronic configuration is 4s to 3d1. So D1 we expected. Titanium D2, vanadium D3, fine. Chromium, when it is coming, we are having here D5 configuration. So this is one very special. Chromium electronic configuration is 4s1 3d5 because of the half field stability D5. Manganese is routine 4s to 3d5. Iron is routine 4s to 3d6, 4s to 3d7, 4s to 3d8. It is again special. We know about all these in atomic structure lesson only. We generally discuss this. So 4s1 3d10. Okay, now copper 4s1 3d10, very special. Zinc is 4s to 3d10. This scandium to copper, these elements are generally called transition elements. These zinc group elements are not considered as transition elements because D block elements means all these are D block only. But transition element, when it comes, we say transition elements are those elements in which outermost two shells are incompletely filled. Outermost two shells are incompletely filled either in the normal elemental state or in the most stable oxidation state. For zinc, the most stable oxidation state is +2. Otherwise, normal state is 4s to 3d10. In such kind of cases, that is in normal state or in +2 oxidation state, you can't see the two shells incomplete. Only one shell is incomplete in case of zinc group. So zinc is not considered as transition element. Zinc is not a transition element, first point. Then the electronic configuration, if you see, ns1 to 2, n-1d, 1 to 10. If I give a chance, okay, now I'll just try to make this ns1 to 2. You can see here 0 is also there. So it is better to mention ns0 to 2. But except these kind of cases, remaining all cases, either 1 or 2, normally 2. Okay, now sometimes it is 1 again. So ns1 to 2, n-1d, 1 to 10. This is for D block elements as well as transition elements. Transition elements also same electronic configuration. Common electronic configuration is ns1 to 2, n-1d, 1 to 10 for both D block elements as well as the transition elements. The general electronic configuration is same. So chromium, copper specialties. We'll go with more. You can see here yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. Here so many interesting things are there. It is expected. Exception 1, exception 2, exception 3, exception 4, exception 5, exception 6, exception 6. So out of 10, there are only 3 normal elements. Remaining all are having an exception. You can see in this period, in this D black series, maximum elements are with D1 configuration. D1, 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 D1. D0 is also there. Palladium is very special. That is having D0 configuration. Okay, this group is very special. Nickel is having 4s to 3d8, but this is having 5s0 4d10, and this is interesting having 6s1 5d9. Okay, now all these are having different outer electrons, outer electronic configuration type, you can say. So this is very special. Here all these are exceptions. Any of this can be asked. Electronic configurations you can't spare. You have to remember this electronic configuration. So here it is better to remember 1, 2 last elements are common. Remaining all are having 1 electron. Palladium is 0 electrons in s orbital. If you remember like that, that will be much easy. Then lanthanum. In lanthanum cases, again, very interesting thing you see, chromium is having 1,5 configuration. Here also 1,5 configuration, but here it is not there better. Okay, here there is no anomalous electronic configuration. This is very common. You see 2, 1, 6s to 5d1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. Up to here there is no anomaly. Here this is the first time we are having a difference. Okay, here it should be 2, 8 actually like this. Otherwise 0, 10 like this, but it is having specially 1, 9, that is the exception, and again this is exception. That is a routine exception, like copper, silver, gold, all they are having D10 configuration, so this you can expect. About these elements we don't know much. Okay, that's why nothing special, only this one is given, a special case. Remaining all are given as it is normal. So electronic configurations, what you need to remember is chromium is having half field stability, copper is having full field stability. In 4D series, many elements are having S1 configuration, very, very special. And in 5D series configuration, there is tungsten. Tungsten is not having similar to chromium. Tungsten is not having similar to chromium configuration. Remember that point. Platinum is not having similar to palladium or nickel. That is again special. Gold is having 110. This is very similar to the copper. Here, no need to discuss much about this one. That's about the electronic configurations. Coming to atomic radius. What are atomic radius important points? Generally, atomic radius down the group increases, cross the period decreases. So when we are discussing in a 3D series or 4D series or 5D series, 6D series, whatever we are going to say, this is a period. In a period, atomic radius gradually decreases. Atomic radius should decrease in a period. Atomic radius should decrease in a period. Yes. Here also decrease is there, but the decrease is not so high as we discuss in case of representative elements, S block, P block elements, whatever the decrease you are noticing, that much decrease is not there. Of course, decrease is there, definitely decrease is there. You can see some radius I have mentioned here, radii in picometers. These values are exclusively taken for NCERT. Okay, so just for reference purpose, we don't want to do much things on here. 164 is here. You can see here, this is 164, 147, 135, 129. Up to here decreasing. 137 sudden increase is there, manganese. Then 126, 125, 125, 128, 137. So almost if you see the first element and the last element, there is a decrease. In between there are some exceptions like manganese is having. So these I have given for radius of the metallic state beta. If ions radius if you are taking, again there will be some differences. But there is no need to remember much. They don't ask you that which is having highest in the 3D series like that. No stupid questions. Don't worry about them. Maximum line is what happens to the atomic radius in a period. Okay, in a 3D series. In a 3D series, from this element to this element, it will be continuously decreasing. Generally, what happens is that for the last element, okay, now for the last element, that is what we are having, zinc case. Because of the presence of full electrons completely filled, there will be electronic repulsions and size gradually. There for zinc case, zinc, cadmium, mercury cases, sudden increase will be there. This part we were discussing even in P block elements also. Okay, in normal cases also, up to fluorine, up to halogen, the sizes will be gradually decreasing, atomic radius decreasing, and then for noble gases, that will be sudden increase will be there. Similarly, you can notice here. Coming to the groups, scandium, yttrium, lanthanum, actinium, if you see, it is a group, the radius should increase, it increases, no doubt in that one. When it comes to titanium group, titanium to zirconium, the radius is increasing, absolutely fine. But zirconium to hafnium, the radius is almost same, and hafnium to rutherfordium is also almost the same. The reason for this is not only here, except scandium, yttrium, lanthanum, actinium, for the remaining all, 3D to 4D radius increases, 4D to 5D and 5D to 6D radius is going to be almost the same. The reason for the similarity, the similar sizes, similar radius is, after lanthanum we have 14 lanthanides, after actinium we have 14 actinides. We have a term in periodic table lesson we were discussing, lanthanide contraction. Lanthanide contraction means in lanthanoid elements from cerium to lutetium, the differentiating electron is entering into the 4f orbital. Okay, let us say this is the nucleus, this is 4f orbital, and after this we have 6s orbitals like this. So the nucleus power, if it is completely stopped by the 4f orbitals, then these are not under the control of nucleus, so they can go little away, the radius should increase. But practically what's happening, it is not screening properly, so the nucleus power is working on the outermost electrons and they are pulled inside and the radius gradually decreases. This is what we are calling lanthanide contraction. The same thing you can say in case of actinoid, that is as actinide contraction. So here, because of that lanthanide contraction, the effective nuclear charge is going to be more. When the effective nuclear charge is more, that effective nuclear charge is working still in all these cases, in all these elements. So down the group atomic radius should increase, but because of effective nuclear charge, radius should decrease. It should increase, regular trend. It should decrease, lanthanide contraction. When both are working, it is almost the same. So 3D to 4D radius increases, 4D to 5D the radius is going to be almost same, 5D to 6D also the radius is going to be almost the same. So this point you need to remember, that's it. Then ionization potentials down the group decreases. Here same thing, scandium to yttrium, yttrium to lanthanum, lanthanum to actinium, ionization potentials decreases. No doubt in that one, that's true. But when you see titanium to zirconium, radius increases, so IP decreases. Zirconium to hafnium, radius is same. Okay, radius is same, so ionization potential is not decreasing here. Ionization potential is going to increase because of the increase in the effective nuclear charge. So 3D to 4D, radius increases, IP decreases, but 4D to 5D and 5D to 6D, the radius is going to be almost the same. Ionization potential increases. There may be some exceptions, don't worry about them much. Across a period, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, radius gradually decreases, means effective nuclear charge increases. When effective nuclear charge increases, obviously the ionization potential increases. Ionization potential increases. But the increase is not so high like transition, like representative elements. These are the transition elements. Transition elements, of course, increase is there, but that increase is not so high like our representative elements, like our S block and P block. Next point is chromium manganese. If you see, for chromium IP1 and manganese IP1, if you compare, manganese IP1 is greater. When it comes to IP2, chromium IP2 is greater. This kind of points we were discussing in sodium and magnesium. Sodium IP1 is less, but sodium IP2 is greater because it is getting stability. Same case, chromium after losing one electron, D5 configuration, stability. Copper case also same thing, copper and zinc. Copper, definitely copper is having 4s1 3d10 and this is having 4s2 3d10. After losing one electron, it gets stability. So first ionization potential of zinc is more, but second ionization potential of copper is more. That point is to be noted. So what are the lines to be remembered? Ionization potential across the period. Ionization potential across the period increases, of course increases, no doubt. Down the group decreases, but 3D to 4D only, 4D to 5D and 5D to 6D. There are some special cases that in general you can remember it is not going to decrease. Sometimes it is same, most of the times it increases. That's about ionization potentials. After ionization potentials, we have atomization enthalpy. You can see this point here, 326, 473, 515. The more atomization enthalpy you can notice for vanadium, then decreasing, then slightly increasing, then again decreasing. Atomization enthalpy indicates the strength between the atoms like that, and here atomization enthalpy is maximum for vanadium. Just remember this point, atomization enthalpy in 3D series is maximum for vanadium for our internal exams only. Okay, now final NTA exams, final JEE mains exam, they don't ask you the memory based questions. Okay, now purely memory based questions they won't ask you. Next is melting points. I didn't mention here. Melting points actually depend on number of electrons. Number of unpaired electrons, if they are more, the melting point is going to be more. So scandium to chromium, the melting point increases. Up to here it will be increasing. Then up to manganese it decreases. Then of course increase decrease will be there. But the peak points will be chromium only. 3D series chromium, 4D series molybdenum, 5D series tungsten. They will be having maximum melting points. We know about tungsten. Tungsten melting point is so high, that's why we are using that in bulk filaments, right? So atomization enthalpy and melting points, both things I am explaining. And atomization enthalpy is maximum for vanadium. Chromium, molybdenum, tungsten will be having great melting points in 3D, 4D and 5D periods, series respectively. So this is all about the introduction, you can say. These are the groups. 3rd B group, 4th B group, 5th B, 6th B, 7th B. These 3 groups are together called 8th B group. This is 1st B group, this is 2nd B group. The 2nd B group elements are not considered as transition elements. We were noticing this point already. The general electronic configuration is NS1 to 2, N-1D 1 to 10 for both D block elements as well as transition elements. Okay. So 3rd B group is nothing but 3rd group. This is 4th group. IUPAC notations, if you see 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay, now each series are having 10 elements. After 100th element, we are generally giving the names as U, 111, unnium, 100 if you want, unnil, nillium, 101 you want, unnil, unnium, unnil, bium, unnil, trium, unnil, quadium, unnil, pentium, unnil, hexium. Okay, unnil. Okay, now UNH, unnil, hexium. UNS, unyl septium. Okay, now there is no hept, there is sept word. Okay, this is about the D block elements introduction part. We have color property, magnetic property, and some other properties. Potassium permanganate, potassium dichromate. We'll discuss about them in coming classes. Till the time, bye.